slow down a little bit, make sure everybody has complete confidence with binary, hexadecimal, and translation decimal. And also the adders, the half adder and the full adder. We need to do a little bit more about that. I squeezed them in at the end. So let me do that first, since that's the last thing in your notes was the full adder. So what I didn't show you is how to build a full adder. It's not really something you have to memorize, how to build a full adder, but you should know and have it in your notes at some point. So I won't do too much of it, but I'll show you that it works on at least one example maybe. So let's start with this. How to build. So first, let me review what the half adder is made out of. So recall, this is just briefly in the notes. Yeah, the half adder is with and exit. Split, and putting next one. This is the half adder, which we did back a ways, but just for review, the way that works is that it takes two 1-bit entries, P and Q, and it does two things. It does and it does XOR. XOR gives you the sum, but and it gives you the carry. So if you put in 1 and 1, then I should put just sum and carry here. Put carry and sum, and this is the H adder, half adder together. You put in 1 and 1. You get that 1 plus 1 is equal to 2. So 1 plus 1 is equal to 2. That means that the sum should be a 0 and the carry should be a 1. Another word for sum and carry is always going to be the sum is going to be the ones place. And the carry is going to be the twos place. So if you put in, the rest of them are easier. Put in 1 and 0, there's no carry, right? There is a sum. 0 and 1, same thing. And 0 and 0 gives you 0. Okay, so for a full adder, that's why you call that one, why that one's called a half adder, is that I never explained why that was true. Because you need 2 of them to build a full adder. So if you need 2 of them to make a full adder, then we should call it a half adder. So, so here's how you build a full adder. Full adder takes in 3 P, So it does half adder on both of them. So, on both pairs. So P and Q get added together with the half adder. So you get out a carry, a sum, and then you just keep the R and wait and put that in with another half adder. So you take the sum from P and Q, and that gets added in again to another half adder. And then the interesting part is that if you have a carry from either of them, then you should carry it all the way. So the two carries, you have possible two different carries, but if either or work, just a regular or, you don't need XOR. It's either of them or both of them turn out to have a carry, then you let that be one of the outputs. And this one you just keep it. So that's, that whole box is the full adder. And this is the new carry. This is the new sum. Again, the carry will be the same thing as the twos place. And the sum will be the same thing as the ones place. So it's really for your information what's inside these boxes. I'm not going to put on a test that you have to remember it by memory. And I guess it might be that important, but I just haven't ever done it before, so I probably won't now. So not on the test, but you should have it in there in your notes so that you can find it and know that that's why it's called a half adder, because you put two of them together to make a full adder. But then you also need an extra or at the end there, not exclusive or, just a regular or. So let's see how it works, at least for once. Like if you do the full adder, and usually I'm just going to shrink it down to a box that looks like full adder. It has three inputs, P, Q, and R. They're all 1 bit, so the most that you can get is 1 + 1 + 1 = 3. Yeah, question?
Could you show us a truth table of this?
Yeah, a truth table for it would be good to have too, just to know. Yeah, we did, last time we did the algorithm for it, but truth table would be good to see the whole thing, so you can look it up. And we can work out some of them using the circuit here. Like, so if I have PQR, and so this would be the carry and the sum here for a full adder. So if I put in 1, 1, 1, so let's just try it. Put in 1, 1, 1 up here. Then I use the half adder, and I get a carry and a sum. So for that, I do try not to look at the truth table. I think 1 + 1 is 2, and that means the carry is my twos place, and the sum is a 0. This one goes all the way in over here. Now I do another half adder. 0 + 1 into the half adder gives me 1. So I have no carry, 0, but I have a sum of 1. And then I look at the OR for the 1 and the 0 going into the OR. So it'll be a 1 coming out. Because either one into OR gives you a 1 coming out. And this will be a 1 coming out too. So it worked. I got a carry of 1 and a sum of 1. And that's what I'm supposed to get, because checks off, since 1 + 1 + 1 = 3 is what it's supposed to do. It's supposed to add up the 3 bits going in. And 3 in binary is 1, 1. Yeah. So it's supposed to give me the answer of the addition in binary. And that's why it has a carry and a sum, two's place and the ones place. So that's why you don't have to memorize the circuit to work it out, or the truth table to work it out. Because the algorithm is that the full adder is just gonna add the 3 bits like normal addition, ones and zeros, and then your answer will be either 0, 1, 2, or 3. And you can always write those as a ones place and a twos place. Here's the rest of them now. So if you had in 1, 1, 0, or 0, 1, 1, or 1, 0. Well, what is the normal way that I write this? I try and stick to it. Let's do 1, 0, 1, and 0, 1, 1. So actually, all 3 of those are going to give you the same carry and sum, because they're all adding up to give you 2. 1 plus 1 equals 2. So you can try them on the circuit, but they will give you each carry of 1 and the sum of 0. Think through one of them. Meant the R is 0. Then that last one would be a 0. Everything else would be the same. Yep. That seems to be working. So these are all adding up to 2. Yeah. Then the next group would all be like 2 zeros and a 1, so they'll add up to 1. So it'll be like 1, 0, 0, 0, 1, 0, 0, 0, 1. And then the last one will be 0, 0, 0. But these, well, my lines are not great today. Good enough. These 3 all add up to 1, so they'll have a sum, a 0 carry, but a sum of 1. So these are all since 1 plus 0 equals 1. And that does equal the 0, 1, as in no carry, no 2's place. And finally, yeah, 0, 0. Since 0 plus 0 plus 0 equals 0. Or 0, 0. The output's always like a 2-digit or a 2-bit output. So you get 0, 0, and know that that's supposed to be 0. Yeah, makes sense? So full adder and half adder both do the same thing, in other words. You don't have to like memorize 2 different setups. All they do is they add them together and then give you the 2's place and the 1's place. You just have to know how to do binary numbers for them. So it's if you know how to do the binary numbers, then you know how to do the half adder and the full adder. If you remember, that's all they're doing. It's just adding them up. So we should do some more binary numbers. And then the hexadecimal numbers too. So and there's a couple of shortcuts that I didn't really do very much of yet. So if you did the quiz already, then that's fine. You may have done it the long way, but now you'll know a shortcut so you can do it the shorter way. So let's do, just for review, the first one, translate a binary number into a decimal. So like 1, 0, 1, 1, 0 from binary to decimal. All right. So it's good to have that list of powers of 2 written down somewhere. I always put up a list of powers of 2 over here. I've got 1, 2, 4, 8, just doubling over time, 16, 32, 64, 128, 512. Oh, why did I keep doing that? I'm so happy to get there. 256, 512, and 1024. That's a pretty good list. I mean, this is the one that's kilo, because it's close to 1,000. So you could use it for kilobit or kilobyte, and that always means 1024 really instead of actual 1,000. So we end up using powers of 10 to describe things like giga and mega. Okay, so this would be 0s, 1s, 2s, 3s, 4 powers. And I guess it might be just as well to start on the far right. So I'll start there, and that equals 0 times 1 plus 1 times 2 plus 1 times 4 plus 0 times 8 plus 1 times 16. So the whole number is equal to that sum. And I just drew that arrow to show that I'm starting on the right and counting up. So 0 times 1 is the first thing, and then the 2 1s are 1 times 2 and 1 times 4. Then a 0 times 8, and then finally a 1 times 16. Now I have to be careful not to actually accidentally count some of the ones that are 0s. So I'll go ahead and cross those out. Like that's a 0, that's a 0. So all that's left are the 2, the 4, and the 16. So adding those up gives me 22 in decimal. Okay, and so now we should go back. We haven't done much of those yet, so I should do a couple of those maybe. Translate one that I haven't done yet, like, I know, here's a good one. Translate 127 from decimal to binary. This will turn out to be a nice shortcut that you can use, because it's 1 less than a power of 2 up there. So I'll go ahead and do it like we did last time for, following the steps for this, but then I'll mention a shortcut. That always happens. It always turns into a string of 1s. But the method was to look for the largest power of 2 that fits into your number, your decimal number, is not bigger than it. So find the biggest power of 2 that's no bigger than my number, than 127. So 128 would be great, but it's too big. So I do 127 is equal to 64. But what's left over is 63. So I write it as the biggest power of 2 that's no bigger than it, plus whatever's left. That's 120 plus 7, yeah. And then you do it again, you find with the remaining, with whatever was left over, the remaining part, you find the biggest power of 2 that's no bigger than that, and fit it in. So you repeat this process for the remaining part. Find the biggest power of 2 again. That's no bigger than that. this time it'll be no bigger than 63. But in general, it's whatever's remaining. So, I'll say it's equal to 64 plus, and now look for 64 would be great, but that's too big, so I have to use 32. And then what's left over is 31, because 32 plus 31 equals 63. And this keeps happening. Every time I get the remaining part is 1 less than the power of 2, because I started with 1 less than a power of 2. Like 127 was 1 less than 128. So half of it splits almost into 2 perfect powers of 2, but it's 64 and 1 less than a power of 2. And then every time you have 1 less than a power of 2, it splits into a power of 2 and 1 less than a power of 2. So you keep on repeating this and you get 64 plus 32 plus 16 plus 15, that's the 31. And then 64 plus 32 plus 16 plus 8. Okay, I'm just going to finish that off. The 15 is 8, but then you could do plus 4 plus 2 plus 1. You could do 8 plus 7, but then I did it in my head. 7 equals 4 plus 3, but that's 4 plus 2 plus 1. Maybe I should show the rest of the steps there. Keep on doing it. And every time you get 1 less than a power of 2. So what happens is you use all the numbers. You get, for 127, you use 64, 32, 16, 8, 4, 2, and 1. So the binary version of that is just going to be 1, 1, 1, 1, 1, 1, 1. So I'll put it down here, but it's 1, 1, 1, 1, 1, 1, 1, right? 1, 2, 3, 4, 7. 7 ones in a row. In binary. Make sure you get 7 ones in a row there. So that's a finding the biggest power of 2 that fits into it, and then looking at the remainder, finding the biggest power of 2 that fits into that, and looking at the remainder, is the way you usually do it. And that'll give you a unique answer every time that you can then double check if you want. But if you do start out with a number that's 1 less than a power of 2, it's always going to give you a string of 1s. So I think we mentioned that shortcut before, but here it is specifically. Like this happens every time. If you work whatever and the number of 1s is always the same as the power of 2 that you worked on. So here's that shortcut. 2 to the n minus 1 in binary will be exactly n 1s in a row. So whatever the power was, like that was 127 was 2 to the 7 minus 1, I guess. Yeah, because 2 to the 6, 2 to the 5. Yeah. 127 equals 2 to the 7 minus 1 equals 1, 1, 1, 1, 1, 1, 1. So one little shortcut that's nice. The other shortcut is for hexadecimal. So far, all we have, I did mention that there was one, but I didn't show you how to do it. So far, all you can do is, if you're going from hexadecimal to decimal, then you use powers of 16. So, review that. Let's see. did 2 examples, so third example here would be translate a quick hexadecimal number like 2D from hexadecimal to binary. This one's not too bad. So it's 2 times 16 plus 1 plus D times 1. That's the 16's place and the 1's place. But D is actually A, B, C, D, E, F is 13. I gotta write it down. So for hexadecimal, put it here. 0, 1, 2. All the regular numbers mean the usual thing, 0 through 9. But then you have A, B, C, D, E, F. And those are 10 through 15. So 10, 11, 12, 13, 14, 15. I almost always have to write that down for myself so I can be sure that I have it. So D is actually 13, so this would be 2 times 16 plus 13 times 1. So that's equal to 32 plus 13. 32 plus 13 is 45. I was thinking hexadecimal to decimal, and then for some reason I wrote hexadecimal to binary. We could do that. I'll do both. So this is in decimal. So put decimal there, and then I'll do binary too. That's correct, right? So 32, yeah, plus 13. That's about as big as I'll make it, unless you have a calculator and you can do the larger ones on a calculator. That's about as much as you'd have to do for hexadecimal to decimal. Okay, now for hexadecimal to binary, I'll do that same one. I'll show you the shortcut. And then we can double check it that it gives you the same decimal by the shortcut. It's because hexadecimal is base 16, which is of another power of 2, that you can go really fast between them. So, since 2 to the 4 equals 16, we can translate hexadecimal. I'm going to start abbreviating that with just that hex to binary and back by just using groups of 4. And it'll be groups of 4 bits in the binary number. So you need to see what I mean by that. What it's going to be is that you just treat each group of 4 as if it's just a 4-bit number, and you find that instead of having to work on the whole thing. Let me do an example though. So translate this binary number 1 1 0 0 1 0 1 1 0 1 1 1 0. Okay, it looks huge. From binary to hexadecimal. Just hex is fine. Okay, so it says you can use groups of 4. So here's where the groups of 4 come from, though. You start at the right-hand side and split it into groups of 4. So first 4, second 4, third group of 4. And the last one, you always end up with some, you might end up with some blank space because, you really need to work from starting with the zeros place. So you might have some leading zeros. You can just fill these in with zeros if you want. This could be like 0, 0, 0, 1. So split into groups of 4. 4 bits, starting at the right. Okay, so each 4 of them, I just turn it into a number that I recognize. So if you're really good with hex, you can turn it directly into a hex number. But I like to turn it into a decimal number and then look at my hex numbers from 0 to 15. So for instance, 1110 in decimal is going to be 2 plus 4 plus 8. So that equals 14. So 14 in hex is E. So that's 14 in decimal, but then the whole thing turns into E in hex. So then you do that for each group of 4. So what I'm going to do, I'm treating each group of 4 as if it's just representing a number from 0 to 15. So I split it into those groups of 4, so then I treat each group like a number from the 0 to 15. So the next one would be 0, 1, 1, 0, so it'd be like 0 plus 2 plus 4. So 6. So that's a number from 0 to 15, but it's one of the regular numbers. It's not a 2-digit number. So all the 1-digit numbers, you just keep them. So I just keep 6. Then 1001, that's 8 plus 1, so 9. So I keep it. And then if I have at the end there, I don't have 4 of them, but I still treat it like a binary number and read it from the right. So that actually is just a 1. So you could put in zeros here if you want. Yeah. 0, 0, 0, 1. So you don't really need them. But if you need a note, you could say, think 3 leading zeros here. Okay, then finally, you just string those numbers together, and that's your answer. 196E is the answer. In hexadecimal. So these are like the steps. This one's a step. This is a step, and then now just string them together. So it's a 3-step process, sort of. You can kind of shorten it if you can do some of those in your head, or write the 196E closer together instead of spreading it out like I did. But that's how you do it. Okay. So I have no idea what either of those numbers is in decimal, like the normal numbers. It's something huge though, right? It's probably in the millions. but I haven't worked it out. But you can go directly from binary to hex just by chopping it up into groups of 4 and doing it. And that explains why it's great for computers. Computers just use binary, period. But for humans, it can be really fast to type in 196E or to use them as codes for something like the color wheel. And then the computer can translate it real fast from 196E to the string of 1s and 0s, or from the string of 1s and 0s back to 196E if it's trying to talk to you and give you output. And because it can just work one hexadigit at a time and go directly to it, so it doesn't have to do that whole long process of finding the biggest power that goes into it and so on. You can just do it on a small bit, small groups. Yeah, so you can go backwards too. To go backwards, you just take each of the hexadigits and turn it into a string of 4. So I should do that. I'll do that with the other example there. See if we get the same number. So this would be like, oh, I didn't remember to use the top number. Let's do example 4. So example 5 for today would be translate. Back. I'll do that one again. 2D from hex to binary. And then make sure that you can double check it. So for the giant number like that one that I just did, it's pretty hard to double check it any other way than just looking at it again to make sure I didn't make a mistake somewhere. I did it pretty slowly, so it came out looking correct. Yep. For a small number, I can double check it by finding the decimal. So for each digit, I make a string of 4. Hexadigit. So for those, you have to make sure that you put in the leading zeros if you need them. So you have to use all 4 bits, even if it's a number that's smaller than 15 or smaller than 10 or something. Zeros, so the zeros in front. I don't know if this one will have a good example of that, so I'll put an extra example here. Like if you see 3, you should make 0, 0, 1, 1. You know, it's 3 because it's 1 plus 2. But you got to make it with 4 bits, so you have to put in the extra zeros. So for this one, I'll have a 2D, and so the 2, I will make it into 0, 0, 1, 0, and the D, I gotta look over here, it's 13. So 13. So now I have to do another little small translation to binary. If you do them enough, you probably have it memorized. 13. The biggest binary number that goes into that is 8, but it's 8 plus 4 plus 1. 8 plus 4 plus 1 is works. So you put in 8, and what's left is 5. Yeah. So you got to figure it out as a sum of powers of 2, which if you have to do it slowly, just figure the biggest one, which is the 8, and then what's left is 5, The biggest one that would go into that would be a 4, and then what's left is 1. All right, so 8 plus 4 plus 1. So that string would be 1, 1, 0, 1. Has no 2s, so it has an 8, a 4, no 2s, and a 1. So now my final answer is just to stick those together. So you could say concatenate them or string them together. String them all together again. So the answer is, now here I don't really need the leading zeros at the very, very front. If you left them on there, I wouldn't count it wrong, because computers always have the zeros on there. But you can drop the leading zeros if you want. Just the ones in the very, very front. So it'll be 1, 0, 1, 1, 0, 1. So that's 2D from hex in binary. All right. So I should double check that really gives me 45. So it'd be 1 plus nothing here. I mean, it's already true. We got it here from the well, this we have to work out what that's from. Okay, so double check. That equals 1 plus no 2s, 0 times 2, plus 1 times 4, plus 1 times 8, plus 0 times 16, plus 1 times 32. Yeah. So the 32's place gave me the right amount to just come out to 8 plus 4 plus 1 again, so it equals 45 in decimal. And that shows you why this shortcut works from hexadecimal to binary and back. It works because when you change that 2 into 0010, it's already got 4 spaces in front of it, so it's already in the 16's place and the 32's place. The 2 here is in the 16's place, so it since it's already got 16 2 to the 4 in front of it, it's like it's multiplied by 16. 2 times 16 is the same thing as 10 times 16, which is the same thing as 10 0 0 0 0. Okay, now, you don't have to prove it all the way, but to see why it works, you can put a note. This works since 1 0 0 0 0 0 is equal to 1 times 32, and this is in binary, but that's equal to 2 times 16, which looks like exactly what we have there. 1 0 times this 4 gives you the 16. That's all I need to say. So whenever you put 4 of them in together, that gives you another power of 16. So a group of 4 bits in binary gives you a power of 16 in hex. That's the best way of saying it. So that's why you can just translate each group of 4 into a hexadigit. Maybe one more. Let's see. Or you could look at the quiz and see if there's any other questions on there, since almost out of time. Then you've got a good bunch of examples for the first two problems on the quiz, translations. Then there's number 3. That one you have to look back in the notes a little bit. We did example like this, I think Wednesday or Thursday last week. So it's got a circuit, and it asks you to do 2 different things. First, it asks you to write the circuit as a logical statement. So you have to like take the P and the Q and carry them through the circuit. The first thing would be P or Q, because it's got an OR gate. So at the end, fill in the blank, the logical statement X is going to be a big long list of P and Q. It'll have P and Q so P or Q, and not, I can't figure it out in my head. You have to actually put the P, Q through the circuit, figure out what the logic statement is. Then it says you're allowed to fill in the rest of the table using either method. So one method is just to put P and Q as 1 and 1 on the circuit and then trace it through, which is the same thing as you have to do for the last question on the quiz, number 4. Just put 1 and 1 and then put 1 and 0 each time, figure out what X is for the given inputs. You can do that just by using a pencil on the circuit once, then maybe erase it, do it again, then, or you could draw a separate one if you wanted to. If you use the logic statement, if you're sure that you've got it right, you can show your work and then show the whole table for steps, like P or Q. So either way you do it, if you do it by tracing the 1s and 0s through the circuit, you can just write your answers in the X column, and you don't really need to show any work in between. That's just space left there in case you wanted to use the method of doing it with the whole logic statement and doing it step at a time. But you can totally just trace each pair of inputs all the way through the circuit to get it. Any question on the quiz? So I could do some more examples like these. I don't have time today, but I could do them tomorrow if we need to. I think we have examples in the notes already, but more is always better. Okay, good. Yeah, see you on Teams tomorrow then. That's it for today.